Let's open the floor for questions on the material that we discussed so far. Questions on the material that we have discussed so far? Yes.
So I had a question about transfer functions being precise or not. So we discussed an example of constant propagation, and there were two families that were defined for transfer functions. We said the other one was more nuanced, and we said it is more precise. So how do we define the preciseness of transfer functions? Preciseness of solutions is fine, but what does it mean to be for a transfer function to be precise?
Okay. You know, I didn't mean to use the term precision in a very formal way, although I'm sure it can be used in a more formal way. Let me try to answer this question, right? A transfer function is more precise if it produces more precise values for the same statement, right? So if there are two transfer functions, f1 and f2, for the same statement, if it is true that, you know, for any statement, if it is true that, and for the same input x, if it's true that f1 sx is greater than equal to f2 sx, recall that in the semi-lattice, one value is less than equal to another value if it is less precise or more conservative than the other value, right? So if f1s is always producing values that are greater than equal to f2sx, then I can claim that f1 is more precise than f2. Does that make sense?
Yes. Yeah. So it's essentially based on the solutions. There's no other property of the transfer function for it to be precise.
Just the solution it produces, right? And that's it. Yeah.
That's it.
For example, in the constant propagation example, if I use z equals x plus y, then one of the transfer functions would just say bottom, and the other one would try to give you a higher answer, you know, a better answer, if possible.
Okay. Thank you.
Yeah. Okay. Anirudh?
So I had a doubt in the proof of where we proved using induction that data flow, that the fixed point iteration will converge if the data flow framework is monotone and has a finite height. In the base case, we proved that we said that the value after the first iteration are no greater than the initial values, and this is trivial because all the initial non-boundary values are top values, and they can only go down, which is fine. But what can we say about the boundary values? Like, we don't know what those are, and how can we say that those are no greater than the after the first iteration?
Okay, see, if the boundary values are at the boundary, which means, for example, in a forward DFA, they don't have any incoming edges, then the boundary values never change throughout the program, right? Similarly, if it's a backward DFA, then there are no outgoing edges of the boundary value. So they will never change throughout the DFA, and that also holds for the first iteration. And so we can just say that, okay, you know, they're less than equal to after the first iteration. I mean, that's a simple answer. I wonder if that's what you were looking for, or yeah.
Okay, so that is a criterion for the boundary values. Okay, so that okay, I thought like it could be possible that the first basic block might have a loop into it or something. That cannot be possible for a boundary value block.
Yeah. So if the first basic block has a loop into it, then we just create a dummy node in front of it that just basically serves as a boundary value. Yeah.
Okay, sure.
That's a good point. Yeah, absolutely.
Okay, so there is only one entry point.
There's only one entry point, and it, you know, and it doesn't have any incoming edges. Yeah.
Okay.
Okay. Jay.
Yeah. So I have a few questions. When we discuss about the distributivity of a framework, I mean, what implications does it have other than let's say saying that the MOP solution is same as the MFP solution?
So that is the primary implication. I mean, actually, you can actually even, I mean, it's you know, I would imagine that it's a bijective relation that, you know, if the MFP solution is an MOP solution, then the for all possible programs, then it must be true that the transfer functions are distributive, right? So So basically that's the idea that the program has, one way to think of a program is that it is it has control flow and you think of it as a graph, and another way to think of a program is that it's a set of paths. In that case, you're not thinking of it as a graph. And the kind of significance of the MOP solution or the distributed solution is that, irrespective of how you think about the program, whether you think of it as a set of paths where you completely unroll the entire program and kind of separate it into all the possible paths that you can have, and notice that number of paths can be infinite, still the answer is going to be the same as that you would got for the completely packaged control flow graph. Right, so that's pretty much the significance of distributivity. I also wanted to say one word about the ideal solution. Notice that the word ideal is a really strong word, but it really doesn't mean that it's the best possible solution for constant propagation. No, that's not what ideal is saying. Ideal is saying that for these set of transfer functions, for these set of values, for this neat operator, right, then this is the ideal solution. Okay, it's not, I mean, you could have changed the transfer function, made it better, and you would have a different ideal solution. Okay, but for a fixed set of transfer functions, for a fixed meet operator, and for a fixed set of values, of course, this is the ideal solution. And the ideal solution basically can reason about what are all the paths that can reach here, and then give you a conservative answer of what is the, what is the best I can say about this program point. Also, notice that the entire DFA framework is kind of constrained by the fact that it has to give one value to every program point. I can't say that, at this program point, if I came through this incoming edge, then this is the value. If I came through that incoming edge, then this is the value. Now, those kind of solutions are not acceptable in a DFA framework. Maybe you want to do a more kind of precise analysis, in which case also, ideal is not capturing that kind of thing. The ideal solution is the solution that fits in the DFA framework, which means every program has a single program value. Every program point has a single value associated with it, which is the most conservative value that can ever happen for that program point. And then we want to talk about all the possible paths that can basically reach and all the executable paths. So, I just want to clear that up a little bit. Yeah, and Jay, what's your second question?
So while discussing about the MFU solution, we informally defined an ordering on the solutions. We said that a solution would be less than equal to some other solution. The value at each program point is less than equal to the corresponding value of the other solution. Then we said for the MFU solution that it's the maximum such solution which satisfies the equations, the DFA equations. So is there any way by which we can argue the existence of this of a unique MFU solution which is maximum?
Okay, yeah, that's a great question. So basically, when I say that a solution is a maximum solution, what is the guarantee that there is a maximum solution? Why can't there be two maximal solutions such that the two solutions are incomparable? Maybe, in one point, in one solution, program point P1 has higher solution, but program point P2 has a lower solution, in which case the two solutions become incomparable. And then, the whole idea of maximum solution goes out of the window. I'm not going to do, I'm not doing a full proof or anything like that, but here's the intuitive understanding that if one point is higher, then the other point must also be higher, because the whole framework is monotonic. It can't, it's not possible that, you somehow got a better value for one point and you got a less value for the other point in the ideals, in the maximum solution, right? Because if you increase the value of any one point, it can only have a positive effect on the other points. It cannot have a negative effect on the other point. That's the whole monotonicity property. The meet operator is monotonic and the transfer function is monotonic. And because of that, we basically can be sure that there is a unique maximum, and we can kind of talk about that.
I just had one last question. So while discussing the ideal solution, we said that we consider all the execution paths, and the number of paths can be infinite, possibly due to say in loops, and we don't know how many times the loop will go. And obviously, it's an undecidable problem, but we said that it's a useful theoretical concept at times. So, like in some cases, were able to prune some branches out by trivially saying that this branch won't be taken or something like that. Can we also argue about loops? Let's because most of the times loops get executed for a fixed number of iterations, say n. So in the paths, I'll only consider the loop paths which has n cycles and no other paths. I mean, if we are able to argue about that.
Absolutely, absolutely. So the ideal solution is supposed to argue about all that, right? So, for example, if the ideal solution has an oracle, a magical oracle that can tell that, okay, this loop can only execute n times and never more than n times or 10 times or 100 times or whatever, right? And then I'm just going to meet over those 100 paths and not over an infinite paths, right? So ideal solution is supposed to capture only those paths that are ever executable, right? And it is actually possible to do this. It's just going to be a very expensive computation, right? So for example, I can just keep assuming it's a finite state. So once again, I think we have discussed this before. Undecidability is only for infinite state machines. Almost all machines, actually I shouldn't say almost all machines, all physical realizations of machines are finite. So assuming we have infinite computational resources or unbounded computational resources, I can just keep executing the loop until I've exhausted until I've either determined that it's an infinite loop or I have exhausted all possible states that can be input to that loop, right? So ideal solution is also actually computable if it was a finite machine, which all programming languages and all machines actually, most programming languages and all machines are. Does that answer your question?
Yeah.
Okay. I should point out that we are running out of time. I want to have a bigger discussion. I just want to check how many of us have a class after this. Just raise your hand. So, I mean, if nobody has a class, then we'll continue. If somebody has a class, then we'll figure out what to do. Shivansh, you have a class?
Yes, sir.
Okay. All right. Okay. And do I see more hands raised? Arpit, okay, Arpit also has a class. Okay, maybe we can we'll have another session later in the day. Can we schedule another session later in the day today? Let's say at 12 noon, maybe. Would that work for everyone? Please raise your hand if it doesn't work for you. Arpit. Okay, let's try to schedule. What I'm going to do is I'm going to continue this session. For most people are basically okay with continuing the session. I think we've had a very short session. We should continue it. People who need to drop off, please drop off. You can always view the recording. And then we're going to have another session very soon, before the next week. We're going to schedule it on MS Teams channel to basically continue this discussion and also talk about the other 4 lectures that we have not discussed so far. Okay, so yeah, so I just want to say that let's continue. So more questions?